So these are the constant temperature line. Constant temperature line. So first initially 0.3 bar is mentioned, 0.3 megapascal. So the pressure is equal to 0.3 megapascal. That is nothing but equal to 3 bar. So from the 3 bar, the saturation temperature, from the 3 bar, the saturation temperature is 133.55 degrees centigrade. And this is less than the given temperature, that is 250 degrees centigrade. So that means steam lies in the superheated state. Steam lies in superheated state. Superheated state. Steam lies in the superheated state. Then now you have to, so this is the point 1. So steam lies in the superheated state. That is the point 1. Next one is at what temperature the steam becomes saturated vapor. So that means it is going to become like this one here. This is the point 2. Next point 3. So this is the point 3. This is the point 3. And this is 250 degrees centigrade. This is 250 degrees centigrade. And here we don't know the temperature. And here it is as 80 degrees centigrade. Here it is as 80 degrees centigrade. So this is what you have to find out. This is what you have to find out. So that means what are the things that you have to find? So one thing is you have to find out the quality of a steam. So what is the quality at 80 degrees centigrade? And what is the heat transferred in per kg of a steam in cooling from 250 degree centigrade to 280 degree centigrade. 280 degree centigrade. So in the, because it is the constant volume representation. See, observe this one. So it is the constant volume representation. So in this case, in case of a, that is V1 is equal to V3, that is the constant volume process, where V1 is in the superheated state. So from 250 degree centigrade, what is the V1 value? So that V1 value is 0.7964 meter cubed per kg, right? From superheated steam, SHS, superheated steam. So V1 is equal to V3, and this V1 is equal to V3 means what is that V1 value? This V1 value is 0.7964, and this V3, that is VF3 plus X3 VFG3. So all these values you have to note down at 80 degrees centigrade. Once these things are over, that is the VF is 0.001029 plus X3 is, that is what you have to find, and VG3 minus VF3, that is 3.407 minus VF 0.001029. So if you make the calculation for this case, you will get the X3 value as this one. X3 is 0.234. 0.234. 0.234. So correspondingly, you can get the value of H3, that is HF3 plus X3 HF3. So after making the calculation, you will get the H3 value as 875.9 kilojoule per kg. Then you can also get the H1 value from the superheated value, that is H1 is 2967.6 kilojoule per kg. So connected to that one, we know that d bar cube is equal to du plus pdv. du plus pdv. du plus pdv, right? and we have to find out the heat transfer, that is Q1 to 2, that is equal to H2 minus H1 plus V into, because here this is the open system, that is V into, that is this is VdP, or this V into P1 minus P2 that you can make. So proceeding with the help of a basic thing, then what you will get is minus 1890.2 kilojoule per kg. This is the solved problem from the PKNAC textbook, and try to go through that one. You can get all the things clear. So this is one value, one problem. And steam initially at 1.5 megapascal, steam initially at 1.5 megapascal 300 degrees centigrade expands reversibly and adiabatically in a steam turbine to 40 degrees centigrade. Determine the ideal work output of the turbine per kg of a steam, right? So try to draw the, because for all these particular problems, now you have to practice TS diagram and HS diagram. So once you draw this particular TS diagram, because in this TS diagram, this is what, and two constant pressure lines. So these are the constant pressure lines. These are the constant pressure lines, right? And 1.5 megapascal and 300 degrees centigrade. So that means it indicates that pressure is 1.5 megapascal, that is equal to 15 bar pressure. Corresponding to this one, the saturation temperature is corresponding to this one, the 1.5 300, yes, the saturation temperature. So if you observe the saturation temperature, it is less than the 300 degrees centigrade. So steam is in the superheated state. Steam is in superheated state. In superheated state. So steam is in the superheated state means this one. That is right. If you draw the clearly, once again let me draw that one. So TS, like this one, constant pressure line, this one, right, and the 1 to 2, because entropy in a reversible, so reversibly and adiabatically means it is an isentropic process. So this is 1 to 2, this is 1 to 2, and here this is the 1.5 megapascal, that is a 15 bar, but the temperature here it is 300 degrees centigrade, and it is going to be expanded adiabatically up to 40 degree centigrade. So it is 40 degree centigrade. It is up to 40 degree centigrade. So how you are going to make the calculation for this case? So the direction of the heat transfer is also like this one. So S1 is equal to S2, because entropy remains constant in a reversible adiabatic process. So what is this S1? S1 is in the superheated state, which is at 300 degrees centigrade. So correspondingly, this value is 6.9189 is equal to SF2 plus X2 SFG2. So at this case, at 40 degrees centigrade, SF value is 0.5725 and X2 value you have to find, and this value is from the steam table, it is 7.6845. So you can get the X2 value, that X2 value is 0.826. Then once these things are over, then now come on to the H1, that is H1 is at 300 degrees centigrade. So that value from the superheated steam, it is 30 from the superheated steam table at 300 degrees centigrade, 3037.6 kilojoule per kg, and H2 is equal to HF2 plus X2 HFG2. See here at this case. So you will get the H2 value as 2152.57 kilojoule per kg. Then what about the here? Just ask ideal work output of the turbine. So ideal work output of the turbine is H1 minus H2. So when you make the calculation for this one, the answer is 885.03 kilojoule per kg. Right? So you know the value of H2 and you know the value of H1. So H1 minus H2, then you can get this particular value. Right? So this is how you have to make the calculation. Right? So moving on to the another problem. So steam, it is flowing at the rate of steam flows at 0.8 megapascal, 250 degrees centigrade. Flowing at the rate of 1 kg. So it's a lengthy problem. I'm going to skip this particular problem. So no need to discuss this at first year level. So the next one is the steam flows through a pipeline. Steam flows through a pipeline at 1.5 megapascal, and this particular problem is connected to the throttling calorimeter. This problem is connected to the steam throttling calorimeter. Steam throttling calorimeter, right? And here the idea is that in a throttling calorimeter, then the process is nothing but the irreversible. Process is nothing but irreversible. So try to draw the enthalpy versus entropy, and this is the quality of a steam line, and the constant pressure lines, that is P1, which is at 15 bar or 1.5 megapascal, and after then it is going to be expanded to 0.1 megapascal, that is 1 bar, that is 1 bar, and that is after the throttling process. After the throttling process, the steam has to expand, that is here. So I am going to represent that in terms of a dotted line. So this is the 1 and this is the 2. That means enthalpy remains constant. H1 is equal to H2. H1 is equal to H2, right? And this H2 is in the superheated region. So superheated region. H2 is in the superheated region, right? So H2 is in the superheated region. Then the pressure here. So if you observe that after expanding to 0.1 megapascal, that is 1 bar in a throttling calorimeter, the temperature is found to be 120 degrees centigrade. The temperature is found to be, so this is the temperature line. So that is the temperature line. It is 120 degree centigrade. It is 120 degree centigrade. Find the quality of a steam in the pipeline. Find the quality of a steam in the pipeline. So H1 is equal to HF1 plus X1. HFG1 is equal to H2, which is in the superheated region. Which is in the superheated region. So what is HF1 at 1.5 megapascal? This is at 1.5 megapascal, means 15 bar. So connected to this one, the value here it is 844.89 plus X1 you have to calculate, and HFG1 value is 1947.3 from the steam tables, and these things you have to take it at 1.5 megapascal, that is equal to the H2, which is in the superheated state, that is 2716.2. So connected to that one, the X1 value you can get it as 0.963. 0.963, right? So here what is the, find the quality of steam. Then what is the maximum moisture at 1.5 megapascal that can be determined with this setup if at least 5 degrees centigrade of superheat is required after the throttling for a calorimeter reading. Then how you are going to do that particular task? So in that case, again you have to go for the other task, that is moving on to the different situation. Here the pressures are taking the completely, the pressure is 0.1 megapascal. Pressure is 0.1 megapascal, and the saturation, the temperature is going to get the saturation temperature plus 5 degrees centigrade is mentioned, degree of superheat. So that is equal to 104.63 degrees centigrade. Then you have to draw the another curve. So like this one, where you can get it as in terms of this one. So this is 3, this is 4, right? So that 4 is going to lie at 104 degrees centigrade. That is this is the point as 4, right? When you equate this one, so finally, when you equate this particular case, finally you can get the value of X3. So that X3 value is 0.94. 0.94. This is how you can find out the thing. Okay. So these are the things, and the last one is steam separating and throttling calorimeter. Steam separating and throttling calorimeter, and in this case, drawing the diagrammatic sketch connected to this particular point. That is, if you observe the enthalpy versus entropy, because for a pure substance, most of the times you need to practice as the enthalpy diagram. So the first one is, this is the line, and the second one is, that is the line, and onto the line, that is, this is the point 1 to 2 separating calorimeter, then 2 to 3, then 2 to 3. So this is the quality of a steam. This is the quality of a steam line, that is H2, right? And this is at 1.5 megapascal, that is the pressure P1. And this is the another expansion, that is after the expansion, it is 0.1 megapascal, 0.1 megapascal. So once these things are clear, then you can find out the quality of a steam. You can find out the quality of a steam for this particular case. So that is H3 is equal to H2, and this H3 is in the superheated region, superheated condition. So that H3 value from the steam tables, you can observe that it is 2696.2 is equal to HF2 plus X2 HFG2. And this is at what condition? You have to note down that value is at 1.5 megapascal. So from this case, you can get the, after substituting these numerical values, then you can get the X2 value as 0.955. Then when you observe the steam separating and calorimeter, then you can find out the X1 value. This is the formula, X2M divided by M1 plus M2, right? So at 70 degrees centigrade, see, at 70 degrees centigrade, the specific volume of the fluid is 0.001023. It is meter cubed per kg. So connected to that one, try to find out here. Try to find out M1. M1 is equal to, that is V1 by VF1. V1 by VF1. I think V1 is given as 0.150 liter. So 0.150, 1 liter is equal to 10 to the power of minus 3 meter cube. So V1 is this one. So that is nothing but equal to V1. And VF1 is at 1.5 megapascal. If you make the calculation, then you can get the M1 as 0.146 kg, 0.146 kg. Then what about the M2? So where this is the M2? So here also try to find out the M2, right? So M2 also, that is V by VF2, V by VF2. So try to make the calculation for this one, and you can get the value of M2 as 3.24 kg, 3.24 kg. Then substitute that M1 and M2 in this particular expression, then you can get the value of quality, that is X1 is equal to, initially first starting you will get it as X2 value, then after then you can get the X1 value. That X1 value is 0.915. So this is how the steam separating and throttling calorimeter problems you can carry out. Right? So this completes all the numerical problem in pure substance. Hope these things are clear. And I think I have discussed all the numerical problems connected to this one. Thank you for listening this particular class. So thank you one and all.